untold millions of miles away in space can be identified by their fingerprints, analyzed by man's ingenuity. This is the starting point of what we are going to talk about today. This is the key to the second great era of astronomy. Man has been looking at the stars for thousands of years, and his conceptions of what they were, of their real nature, were colored, of course, largely by his fancy and by his imagination. And it is only within the last few hundred years that man's mechanical and scientific ingenuity has devised ways and means for him to find out their true nature. Now, we know that every incandescent body in space is producing radiation which streams out from that body in all directions. That radiation travels in a wave motion. The waves are all of the same shape. They differ only in length, and they travel at a constant speed. Some of them are short, as you see here. That shortness, of course, is measured horizontally. Some of them were long ones. Their speed and their shape remain unchanged. They travel at about 186,000 miles a second. They are energy waves. Now, the atmosphere of our Earth absorbs or blocks out many of these waves of various lengths. But there are two windows, you might say, in our atmosphere through which waves of different lengths may pass. Here is one small window which admits waves whose length is between 200,000 and 300,000 to the inch. This wavelength gives us what we call light. This is what we can see, these energy waves between 200,000 and 300,000 to the inch. That is light. That is everything that we see. All color, everything visual comes through this little window. Now, the shorter wavelengths look violet to us. The longer wavelengths look red to us. And the intermediate wavelengths produce all the intermediate colors between red and violet. The colors run red, orange, yellow, green, blue, indigo, and violet, and they all come through this very narrow window. The whole band of radiation which these objects in space produce is called the electromagnetic spectrum, and we shall talk a great deal about it as we go on. There is another window where longer waves of radiation, of energy, come through, and that again we will discuss later on. Now, man had in the beginning only his two eyes to see stars with, and he did unbelievable work with just these natural instruments. Then about 350 years ago, a Dutch telescope maker named Johannes Lippershey, purely by accident, chanced upon the effect which two lenses, one placed behind the other, have upon light which passes through them. This accident of Lippershey's was heard of by a great Italian scientist, Galileo Galilei, who in a matter of hours had built the first telescope. And this is a replica, a model of one of the very earliest telescopes that man ever constructed. This is a model of one of Galileo's telescopes, and Galileo was the first human being ever to look through a telescope at the sky or at anything else. This is a very simple type of telescope. It has a large lens at one end, a lens for admitting the light from an object. It has a small lens at the other ends, a lens for viewing that light and the image that is formed by it as it comes through the telescope. Now, this type of telescope is called a refractor, and here is a diagram which shows how the refractor works. Here is the object whose light we are observing. That light comes to us and is admitted to the telescope by a large lens at the outer end of the telescope. That lens bends the light Now, the scientific word for bending is refracting, and that is why this telescope is called a refractor. It bends the light and brings all the different wavelengths of that light, red, orange, yellow, green, blue, indigo, and violet, remember, to a single point, the focus, where the image is formed of what the telescope is pointed at. Then that image is examined and magnified by a smaller lens placed behind it. And here is the eye of the observer looking through the small lens, the eyepiece, at the image formed inside of the telescope tube. After Galileo's great discovery, man tried to work with lenses. Now, the large lens in the outer end of a refracting telescope has only one function. It is to gather light, to admit light to the telescope. And here is the first type of lens that was used. This is a double convex lens. And you can see its outline there, but here is a cross-section of such a lens, showing its shape, the two outward curves. Now, this lens was not very satisfactory. In larger sizes, it produced beautiful but disturbing lines of colors all around the objects that were viewed. Colors very much such as we get when light is passed through a prism. So man's worked with these things and finally developed a combination of lenses. This double convex lens that we saw, and then a double concave lens. It's difficult to see its shape as I hold it here, but look on your screen. That is a double concave lens, and the combination of these two, plus several improvements, finally made a lens which was fairly free from these rather annoying and unscientific color outlines. Now, a lens must be made of the finest quality of glass, without bubbles, without flaws, without anything to disturb the passage of the light through it. And because light has to pass through such a lens, it can be supported only around its perimeter, around its edges. So that gives an automatic limit to the size which such lenses and consequently telescopes using such lenses may be made. The size limit is 40 inches, 1 yard and 4 inches. And the biggest telescope of this kind which has ever been built and which ever will be built is the telescope, the great refractor in the Yerkes Observatory in Williams Bay, Wisconsin. This has an objective lens, a lens for admitting light, 40 inches in diameter in its upper end. Its tube is about 60 feet, and of course the viewing and observing apparatus are in the lower end of the telescope. Now, while man was struggling with the problem of these little lenses, another method of gathering light and observing it was discovered. This time with the combination of one of the greatest geniuses the world has ever known, Isaac Newton, and an English scientist, James Gregory. They thought that light could be gathered and focused just as well by means of a mirror. And Newton built the first telescope using a mirror as its main component. That is a reflecting telescope. And here is a diagram showing the basic principles of such a telescope. In this case, a mirror is built and placed at the bottom of the telescope, at this end of it. Now, this mirror is the all-important factor, and the whole secret is the curve into which the upper surface of the mirror is ground. This must be a parabolic curve. Newton's mirror was spherical and didn't work. We've learned since that a spherical mirror has its limitations. A parabolic mirror, which is simply a spherical mirror slightly deepened at the center, is what does the trick. That admits the light through the tube of the telescope, reflects it to a focus high up in the telescope, right back along the path at which it enters. In most reflectors, that cone of reflection is intercepted by a flat mirror set at an angle of 45 degrees, which reflects the cone of light out through a hole in the side of the telescope tube where the eyepiece is put and where this image can then be observed. In the larger reflecting telescopes, other systems are also made available, some of them involving the drilling of a hole through this big mirror and other auxiliary mirrors set up in there to give different optical arrangements for various different purposes. Now, of course, man immediately put his ingenuity to work on this type of telescope. And the culmination of years of experiment, of trial and error, of building these telescopes has resulted in the biggest telescope in all the world. Now, here we can see the figure of an average man, say a 6 feet tall man. And towering above this figure and on the same size scale is this model of the greatest telescope that man has ever built, the great Hale 200-inch reflector at Mount Palomar. Really a magnificent scientific instrument, one of the greatest scientific instruments this man has ever built. It has a mirror working on the same basic principle that Newton discovered. This mirror is 200 inches in diameter. Now that is 16 feet 8 inches, an enormous thing. The mirror itself weighs 14.5 tons. It is made of Pyrex, a very common household material, and Pyrex was selected for the same reason that Pyrex can be used for cooking, because it is not too much affected by changes of temperature. The expansion and contraction of such a mirror must be rigidly controlled because its surface must be perfect to about 1/millionth of an inch. The tube which supports this mirror at the bottom and which holds up here the chamber in which the observer works. Incidentally, this is one of the two telescopes which are big enough so that the observer rides in the telescope while he works, is 55 feet long, this lattice-work tube. This is the telescope itself. It is supported by a great metal mounting, and the mounting weighs and the telescope weigh 530 tons, over 1 million pounds. Now, the chief function of a telescope, of course, is that it may be pointed at any part of the sky. And in astronomical work, the telescope must be kept pointed at any individual star for hours at a time sometimes. How can you do that with 530 tons of machinery? Well, that's a problem of engineering and design. And it was solved in this telescope to such an extent that the great Hale telescope at Mount Palomar can be swung through its arc against the motion of the Earth so that it can keep a single star or other object always in view as that star seems to move across the sky. It only takes a motor as big as the motor that runs your sewing machine at home, 1/12 of a horsepower. Now here is a photograph of that great telescope. Here you can see the mirror, the lattice-work tube, and the vast, ponderous mounting, which nevertheless is so beautifully designed that very little effort is required to move it. Now, not every man can have a 200-inch reflector in his possession. This is a 6-inch telescope. That is to say, the mirror at the base of this is 6 inches in diameter. Now, here is a mirror which is smaller, which is 4 inches in diameter. It's a parabolic mirror. The parabola, of course, is so delicate you can't possibly see the curve. But that is the basic unit of this telescope, a 6-inch mirror. The light from that mirror, because of the shape of its surface, is reflected back up the tube of the telescope till it comes to a focus up here. But before it reaches that focal point, it is picked up again by a flat mirror set at an angle and sent out through this aperture where the eyepiece is put so that it can be observed. This is a finding telescope, a sort of an aiming device to enable the astronomer to pick up more easily these faint, distant objects in the sky. Now, what have we got? We have man looking at them with these two telescopes, the only two he had. Then telescopes came into being and pushed back his horizon of space. And then in 1850, something else happened. The first photograph was taken through a telescope. From that time on, the bigger telescopes are used for photography. No one looks through them. This telescope and others comparable in scope are now cameras. And most modern astronomy is done from photographs. You see, the eye can never see more than it sees when it first looks through a telescope. But a photographic plate, the longer it is left exposed to the light from these objects, the more detail it builds up upon it. And man's memory, well, it can't last anything like as long as a photograph can last. There you've got it. You've got the picture. You can see it. And let me show you here. Here is a photograph of a star. In fact, 4 photographs of the same star taken through an astronomical telescope. In this first picture, this is just about what the eye would see, an exposure of just a second or two, and it shows a very faint star, so faint that we have to outline it with lines to identify it. Another picture with a slightly longer exposure. This star seems a great deal brighter, but look what has happened to the background. Here are more stars which were invisible in the first picture because their light has had a chance to build up on the plate. A longer exposure, perhaps half an hour, shows our original star, the same one, terribly bright, and a great many more stars appearing in the background. They were there all the time, but their light had to have a chance to build itself up. And here is one of some hours. The main star is overexposed out of all recognition, but the background stars, they were there. They're there all the time. No one had ever seen them before, but here they come on this picture, discovered for the first time. So we can see that the camera is one of the most valuable instruments that astronomers can use. But there is another instrument, perhaps equal or in some cases even more valuable than the camera. And this instrument is built around the qualities that a prism has and the way a prism will affect light that passes through it. This effect, again, was first seen and discovered by that incredible genius, Isaac Newton. Here is a diagram of what happens to light when it passes through a prism. Here is the prism, here is a little beam of light going through it. The other side, not the beam of light, but a beautiful band of colors. This is the spectrum. And that word comes from the same root word as our word specter, a ghost. This is the ghost of this little beam of light after it has passed through the prism. All the colors are here, all the colors of the rainbow. In fact, the rainbow is a series of little light passing through the little prisms of raindrops. Red, orange, yellow, green, blue, indigo, and violet. The red light waves are the long ones, the violet are the short, remember. And that this principle has been adopted to an instrument called a spectroscope, which admits light through one tube, where the light passes through a prism. Here you can see the prism, the central, the heart of this instrument, and it is viewed through a small telescope here. A similar instrument to this attached to astronomical telescopes opened a whole new field, a world of wonders in the stars. Let us have a look now at the great electromagnetic spectrum that we spoke about very early in the program. Here it is, spread out for us to see. This is the energy spectrum. All the waves of all the lengths occupy this. Now, this very narrow little segment here is visible light. This is what we see. This is light. Let's expand that a little bit. And here we have the band, enlarged, you see. Red, orange, yellow, green, blue, indigo, and violet. These waves running from 200,000 to the inch, 200,000 to the inch to 300,000 to the inch. The long waves are red, the short ones are the violet. And to the short side of the violet, we have ultraviolet, a word which I'm sure you're familiar with, shorter than violet, shorter waves, you see. Then the X-rays, very short waves, which have the power of penetrating materials which are not transparent. Then these mysterious cosmic rays that come to us out of space and whose nature we do not yet fully understand. At the other side, at the long end, we have the infrared, below the red, longer than the red. That's heat. We can feel those waves. We can't see them. Then we have the waves a little bit longer that we use in radar and in television, and still longer waves in broadcasting, and longer ones for sound. There is the whole story. Now, as man began to study these spectra, he began to find out strange things about them. The light that was produced gave him different pictures according to what was producing the light. Here is a diagram showing several varieties of these spectra, these ghosts. Here is one that comes from an incandescent solid, a solid band of colors merging beautifully into one another without distinct borders, just blending, do you see? Now, man found that if he heated a certain substance to incandescence and then passed the light from that incandescent object through a spectroscope, he didn't get this broad band, but he got a definite set of bright lines. This, for example, is light from sodium. And light from sodium always occurs in the same place in front of the same yellow color at any time. So that when these particular lines are seen, anybody who knows the spectrum will say that's sodium, and the material can be identified. Now, in stars, there are dark lines that cross the spectra of stars. And these dark lines fall in the same places, the same locations, in the same colors, in the same distance from the ends and all the rest of it, as the bright lines that are produced in the laboratory. What does that mean? It means that stars, which have an envelope of cool gases around their hot centers where this incandescence is born, are absorbing energy in that same wavelength, that their atoms are vibrating in the same way, and picking it up and reversing these bright lines, making the bright lines dark, but that dark line identifies the same elements. Therefore, we know by the positions of these dark lines, as we see them in the spectra of stars, just what materials are in those stars. And various other indications, their width and their position and so on, will tell us what the temperatures are, how much radiation is exciting these lines. And given a temperature, we have a star's brightness. Given a star's real brightness, we know its distance. You see how valuable this information begins to become, that we get through these little faint lines, this ghost of light. Now, we've set up an experiment over here in the studio. We have several incandescent materials, several materials rather, which we have made incandescent, and we're going to try to show you the lines they produce. Here are four materials. This is mercury, this is helium, or hydrogen rather, this is neon, and this is helium. The light is being passed through a little slit, through a lens which smooths it out, through the prism, and to this screen. These first lines you see come from glowing mercury vapor, which produce two bright lines in the yellow and green regions of the spectrum. You can see the short wave and long wave. The short wave is the V for violet and the long for R. Now we'll change to a hydrogen gas. And see, this should give us a line, very faint line, near the red end of the spectrum. There it is. You can see it right under the R. Do you see it there? That's made by hydrogen gas. Now we have neon, that common vapor which is used in so many advertising signs. That will produce a series of rather broad lines just off the R, beginning to get into the orange field. And finally, we have helium, that rather inert gas which is found in the sun. That produces a line, too, you see, in the orange and yellow sections of the spectrum. Now, these lines, which were found in the stars, the different arrangement of lines in the stars, gave man a basis for a classification of stars by their spectral lines, a spectral classification. And he seized upon it immediately. At first, there were a great many different classes of stars, and they were lettered and numbered according to the alphabet, from A to Z. But it was found that there was a great deal of duplication there, and this was finally boiled down to 10 different classifications: O, B, A, F, G, K, M, R, N, and W. Now, if you want to remember those, there's a very good way of doing it, a little sentence, which astronomers use when they're studying their science. O, B, A, fine girl, kiss me right now, wow. So if you pick that up, if you want, it may come in handy sometime. These dark lines can also tell us a number of other things about the stars. In addition to their temperature, we have noticed that we know that stars move, and these lines tell us how they move. If a star is moving away from us, its motion spreads out and lengthens. The wave, remember the wavelengths, it lengthens it. And the whole system of lines in the spectrum of that star will be shifted toward the red end of the spectrum. You may have heard of the red shift. Well, this is what it is. Conversely, if the star is coming toward us, it is compressing, squeezing those waves. They become shorter, same shape, same speed, but shorter. And the system of lines is shifted toward the blue end of the spectrum. Now, this is very valuable because it tells us which way a star is moving, and by the amount of that shift in one direction or the other, we can tell the speed at which that star is moving down to 1/4 of a mile a second. This effect was first discovered and analyzed by a German scientist named Christian Doppler, and is known, therefore, as the Doppler effect. You've probably had an experience with the Doppler effect. If you've ever listened to it, listen. Do you hear how that train whistle that you just heard and saw, do you hear how it dropped in pitch? That's the Doppler effect. The same thing, sound waves, you see. The motion of that train away from you lengthened out the sound waves and lowered their pitch. So it is with light. They lengthen the light waves and shift them toward the red. This is the famous red shift, and gives us the speed of recession, the speed at which objects are moving away from us in space. So with many other things, we have learned through a study of the spectra of stars. Now, this other window that we spoke about earlier, this is the window that is open to wavelengths considerably longer than those we can see. And these wavelengths we can study and analyze by the very newest branch of astronomy, radio astronomy. These waves can be picked up by what we call radio telescopes, which are really very complicated and tremendous radio receivers. Here is one of them, a great bowl-shaped affair, and you can see it there. Now, these are usually arranged so that they can be pointed at any part of the sky. And one of the biggest of these, the very largest one that's so far been built, is built in England at the Jodrell Bank. Here it is. Look at it. And you can see, if you watch it closely, that it's moving slightly. Well, these can be moved. This is 250 feet in diameter. Now, the information that we are getting from the short waves of energy received through these tremendous radio telescopes is changing the whole picture out there for us, giving us new outlines to the stars, to the great families of stars, to the galaxies, bringing us news of things which are hidden from us behind clouds of dust, because that dust stops the short waves that we can see, but lets these long ones come through, the ones we can hear. And we have even heard messages from one of our own sun's family in space, Jupiter, the biggest planet in the solar system, and one which has a temperature of 150 below zero. You'd think it couldn't radiate, has. And that sound that Jupiter made, invisible waves, but audible waves, has been heard. Listen. Listen to Jupiter now. You'll hear a rough grating background noise. That's the overall radiation. But Jupiter should produce occasionally a high, clear, bell-like note. That's Jupiter speaking to you from 500 million miles. Now, look back for a minute over what we've talked about today. Man has looked at the stars with his eyes, done wonders, learned an amazing number of things about them just through watching and thinking about them. Then came the telescope, and man's horizon, his sky horizon, was pushed back. Untold millions of miles, more things that he never dreamed of, were made visible up there. Then he could take pictures of them and record these wonders for future study, pictures that would last forever and which could be duplicated. We've got astronomy in our photographic cabinets. Then the spectroscope. There we unlock the secrets. We know as much about the star as though we had it in our two hands at a library table, putting thermometers in it, analyzing it, tearing it apart, finding out what it's made of. And now the last window that we have opened is radio astronomy. The whole universe is taking on a new dimension, a new shape. We are hearing more, learning more. We can't say we are seeing, but we are finding out more about it. And who knows what great boundaries will be discovered in this last development.
This is National Educational Television.